Welcome, everybody. Thank you so much for joining us for this evening's seminar, which is entitled Characterizing Powerboat Hydrodynamics and Their Impacts on the Water Column and Lakebed. My name is Bridget Mendel. I am the Communications Director at St. Anthony Falls Lab. I'm just going to share a little bit about the format for this evening. There is going to be a 60-minute presentation followed by about 30 minutes of Q&A. So many of your questions should be answered in the presentation. So we're asking that you hold questions until the Q&A portion of the evening. We'll begin the Q&A by answering your pre-submitted questions, and then we will go to any follow-up questions that you might have and submit via the Q&A function below. And we will open up that function after the presentation. Today's webinar will end at 7:30 p.m. Central. So any questions that the researchers do not have time to answer will be recorded and we'll post those on the Healthy Waters Initiative website along with the entire webinar. And that should be available for you all in a couple of weeks. After tonight, if you have additional questions for the researchers on the study or other aspects of the University of Minnesota's Healthy Waters Initiative, we ask that you send those to the following email address: healthywaters, one word, at umn.edu. So healthywaters@umn.edu. You can find that other places as well, and the researchers will get back to you. Okay, so I'm going to turn it over to tonight's presenters, who are Andy Riesgraf and Jeff Marr.
Thanks, Bridget. Hello, everybody. Thanks for joining. My name is Jeff Marr. I am really glad you turned out this evening. I'm the Associate Director of Engineering and Facilities at St. Anthony Falls Lab, University of Minnesota, and a member of this research team. So all of us involved in this research are staff members at the St. Anthony Falls Laboratory. We're professional researchers and really excited to have you here. I'm going to introduce the team that worked on this and maybe just pop your camera on and give a wave. Andy Riesgraf is a research scientist. He's a lead author of this report and had a vital role in all aspects. Dr. Jessica Kozarek is a longtime research associate here at St. Anthony Falls Lab. Dr. Bill Herb, also a longtime research associate here at St. Anthony Falls. And Matt Luker, mechanical engineer and research engineer here at the laboratory. Before I start the presentation, I have a few quick comments on the current topic of recreational powerboats and their impacts. It's safe to assume that all of you taking time out of your summer schedule are watching tonight because this issue is important to you. And many of you may be property owners on a lake and have seen changes in recent years on how lakes are used, and possibly water quality changes and perhaps limitations on how you can use your lake. Many of you online are owners of boats and possibly even wake boats, and you are hoping to learn tonight about how best to use your boat or have concerns about your ability to use your own boat in the future. Some of you maybe have management responsibilities to your lake or your watershed, your state, or even your provincial water resources. We're thankful to have all of you with us tonight. The question that we wanted to just bring up here at the beginning is, what is our role at the University of Minnesota as a public research institution? And in many ways, our role is very simple here. Our role is to conduct research, produce robust data, and share that data and findings. And that's what we've done in the first two reports that are produced by this team. And we're excited to be able to share the most recent work with you this evening. This is the first time we're presenting the phase 2 work through a webinar. We received a number of pre-submitted questions before the seminar that asked for us to comment on specific lakes or specific situations including legal and policy situations and so forth. And these questions are really outside of our role as researchers. And so we will refer you to your local lake associations, your state DNRs, or elected officials for work and guidance on those things. Our role is not to pick a side in this issue or a position, but to just provide data. And the recommendations that you'll hear about tonight that are in our report, I just want to clarify that those are based on our data and our findings and our professional interpretation of those data. So I just want to set that stage here before we begin. I think that's all I wanted to say. With that, let's jump into the presentation. All right. So let's begin. So let's start with just where we are. For some of you, most of you might be in Minnesota, but for those that aren't, we thought we'd just put up this graphic of the great state of Minnesota. We're located on the Mississippi River in the Twin Cities. So here's an image of Minneapolis and St. Paul tied together by the upper Mississippi River. If we fly in a little bit further, you'll see the feature that is the St. Anthony Falls, 45-foot approximately waterfall that is the origin of the Twin Cities, with a lot of tremendous history. And our laboratory is located on the banks of that falls. It's a hydraulic research laboratory constructed in 1938, and has had a long legacy of environmental hydraulic, and fluid mechanics research. And we're all really proud to work for the University of Minnesota and at this laboratory. So the outline tonight, this talk is going to focus on the phase 2 study. But we're going to start with an overview of the program we call the Healthy Waters Initiative Research Program. We're going to do an introduction to background on boat-generated hydrodynamics, modes of operation, and then we'll dig into the phase 2 study. We'll have a brief summary of the phase 3 work that's in progress, and then we'll transition into our Q&A. And I'm going to pause and just make sure everybody's seeing. Bridget, you're seeing the full presentation, I assume.
Yes.
Yes, okay. I'm just going to make an adjustment here. So what is the Healthy Waters Initiative? It's a program that we established here at St. Anthony Falls in 2020. And the goal is to conduct research that increases our understanding of the influences on Minnesota's aquatic resources, with the goal to help protect, preserve, and improve our prized lakes and streams in Minnesota. We focus on a single research topic, and we do that for several years so we can get deep within that topic. And then we want to serve as a reliable source of information. So many of the problems we envision in this program are applied problems that have direct application to our resources. And we want to be a source for unbiased, high quality, and accessible information. The current program is focusing on characterizing recreational powerboat hydrodynamics, so waves and propeller wash, and investigating their environmental impacts. If you want to find more about our program, here's the website. And I also just want to mention that the origins of the program were out of a crowdfunding program. For those of you not in research world, funding is always a project to try and secure. We put a QR code up here if you're so inclined to make donations. This is something that really helps us out. The funds go directly to our program, and it's used to help us do the communication like we're doing tonight, but also deepens the research we can do. So that's the last of the advertisement. The Healthy Waters program going on right now, like we mentioned, focused on these recreational boats. And we have 3 phases that we have conducted. The first was completed and published in 2022. And it measured the divergent wake waves produced by recreational boats, including both wake surf and non-wake surf boats. Phase 2 we'll talk about tonight, and that in this phase we go underwater where we're looking to measure and quantify the hydrodynamic forces that occur directly beneath recreational boats, including both wake surf and non-wake surf boats, and how they impact the water column and lakebed during operation. And that report was published in July 2025. And under our third phase is underway. This is focusing on characterizing similarities and differences between wind-generated waves, including storm waves and boat-generated waves, and how they may impact the nearshore environment. And that work is in its second field season, and we anticipate a report next summer. So let's talk a little bit about boat-generated hydrodynamics. I have a photograph here of a boat moving across the water surface, and you can see some beautiful waveforms that are generated. So what is important to know for this talk and for the work we're doing about recreational power boats? And we're going to use power boats tonight because we're really looking at boats that have engines and props or jets that are moving them through the water. So recreational power boat is displacing water, and the phenomena that are produced is highly influenced by the boat weight and its speed as it moves through the water. And there's four primary phenomena that we're thinking about that result from this displacement and movement. There's the divergent waves. Again, we talked about that, worked on that in our first phase of work. And in this phase, we're gonna introduce and talk about three additional phenomena. The first is bow stern pressure waves, and that's occurring right at the boat and just behind the stern of the boat. And then there's transverse waves. These are another wave that's shown in this photograph. These are waves that move perpendicular well, they move in the same direction as the boat is moving, but their crests are aligned perpendicular to the boat's sail line. And they, of course, interact with the divergent waves. And then the fourth phenomenon is the propeller wash. So in order for this boat to move forward, right, we need to remember there's an engine, there's gasoline, there's a drivetrain that's converting that energy into thrust that's pushing the boat forward through the water, and that pushes a jet down into the water, and that is termed generally propeller wash. And we're going to look at that in more detail in this study and present tonight. The final point here is there's much more to this story about the hydrodynamics of boats. The field of naval architecture focuses on this a lot, and it's related to the hull shape and hull physics, water depth, the type of boat, all kinds of considerations that we're just not going to get into this evening. Here's a figure that you'll find in our report. It is a summary of all of those phenomena that we observe and think are important to this problem. And I'll just step through them once again with this graphic in mind. The first are the bow and stern waves. So I assume everybody can see my mouse here. Can somebody on my team confirm that?
Yep.
Okay. So we have as the boat is sitting in the water, and it's got weight, it's displacing water as it rests and moves, and that imparts a force into the water column that is felt underneath the boat. And the bow, we break that into two components. The bow pressure at the front of the boat is actually pushing water forward and moving it downward in the water column. And as the boat passes a single point, if you fix your attention on a single point and imagine the boat moving past, as the boat moves past, it's left a depression. And when you get to the back of the boat, that water recovers. It moves upward as a restorative motion, and it's moving upwards and backwards. And that whole process we kind of lump together as the bow and stern pressure waves. So we'll talk about that tonight. The transverse waves is the next phenomenon, and that's happening behind the boat. There are waves that form astern of the boat, and they move in the same direction as the boat itself. And as I mentioned earlier, the crests are aligned perpendicular to the boat's travel direction. An important point here is that those transverse waves are only occurring when we're at slower speeds. Um, and subplaning speeds is how we list it here. So when a boat is planing on plane, the transverse waves are not able to form. So that's an important thing to keep in mind as we go forward here. And the final phenomenon is propeller wash. And shown here in the blue, the propeller wash is very, very complex. It's a rotational phenomenon. It's also got a jet associated with it, but that jet dissipates as it moves. And so it's the thrust that created by the propeller, accelerates water astern in a manner that resembles a turbulent jet-like flow. So another interesting point here is that most modern power boats are exhausting their engine exhaust into the water column very near the prop or within the prop, and that is putting gas, which in the form of bubbles that gets pushed down into the water column, and that actually imparts a lift onto the jet itself into the prop wash. So it's a very, very complex phenomenon. Just to go back one step, I want to show that all of these effects, um, especially the transverse waves, you may see from, if you're in this boat and it's moving along, you can see these from the surface. They express themselves at the surface. But what's important to remember and easy to not realize is that waves have a vertical component that's very important. And transverse waves here shown with the red circles are a wave motion that penetrates deep, that can deeper into the water column. And that's some of what our measurements get at in this work. Okay. A little bit more additional background information here. Let's talk about modes of operation of a boat. And again, we're going to tap into the naval architecture world and talk about displacement. And displacement mode is a term we're going to use to talk about to characterize how a boat is moving and the conditions on the hull of the boat. So displacement modes in this work is defined, and for these boats that we looked at, is really something less than 10 miles an hour. The hull is at maximum draft. It's really supported by the buoyancy forces on the hull. And typical activities include leisurely cruising. If you're maneuvering around, maybe picking up a water skier or pushing away from your dock, or if you're trolling or fishing, those are all examples of displacement mode. Another mode that most people are very familiar with is planing mode, or being on plane. And these, for the boats we're looking at here, speeds greater than 15 miles per hour. The boat's moving fast enough that the forces on the hull actually lift it out of the water and it can ride up on top of the water surface. It's a condition where the drag on the hull is fairly low. It's the lowest condition. And typical activities include water skiing, tubing, wakeboarding, or high-speed cruising around a lake. Now, of course, between these two is a transition. It's termed semi-displacement mode in our work. Um, and it's in, I would say, well, what it is for, I would say, before wake surfing was a transitional condition. So if you were gonna go water skiing with somebody, you would start in displacement mode. You would hit your throttle and your boat would rise up on top of the water. And as it does so, it passes through semi-displacement mode. It is a condition between the two, and it's also a condition where the drag on the hull is the highest possible. There's a lot of force on the hull. The boat is pitched at its steepest angle. And this happens to be the condition that wake surfing seeks to operate. And it's because it does produce a large wave off of the back of the watercraft. And so what's new and what we've said as we talk about this work is I think this is a type of use of boat, a mode of operation that really didn't exist before the sport was invented. We were either in displacement or planing mode, and we're now wrestling with a new use, a new condition, our boats operating in the semi-displacement mode for long periods of time and the consequences and impacts of that. So hopefully that's helpful, and you'll see these terminologies used throughout the presentation. So the phase 2 study objectives here, we want to identify the primary hydrodynamic phenomena created by recreational boats in motion and how they vary with water depth and mode of operation. And I just introduced the phenomena that we're going to talk about. We're going to investigate the penetration depths and velocities of the bow and stern pressure waves, the transverse waves, and propeller wash, and their potential to resuspend lakebed sediments. And we seek to capture underwater and aerial video of these hydrodynamic phenomena. So with that, I'm going to transfer to you, Andy.
Can you hear me? See me? Only one
Yep.
presenter can share at a time. I think I need you to stop sharing, Jeff.
So you are going to share?
Yep. All right. Can you see the slideshow?
Yes.
Jeff? Yep.
Yes. Mm-hmm.
Okay. I'm going to dive into the methods of how we carried out this study. So first of all, the field study site was at Lake Minnetonka. That's about 15 miles west of Minneapolis. It's a large lake, totaling 14,000 acres, 130 miles of shoreline, and it's a very popular recreational lake here in Minnesota. It's not uncommon to go out there and see people kayaking, and then having boats all the way up to, small yachts. The two, um, the two red stars there are our study bays. And if we zoom in on those, we have the red rectangles here. In 2022 is where our study took place in North Arm Bay. And in 2023, we had another field campaign where we tested additional boats in Maxwell Bay. Both of the bays are about 300 acres. If we zoom in on those red rectangles, this is an aerial view of our site. The yellow dots kind of represent our start and end buoys. And just briefly, what we would do is we would drive the boats in a straight line, passing over bottom-mounted sensors. On the left there is North Arm Bay, and on the right is Maxwell Bay. And on the next coming slides here, I'll go a little bit more into detail about what this figure is showing, specifically the ADCP and the ADV and the depths in which they were deployed. So to collect velocity data through the water column and at the lake bed, we deployed acoustic-based sensors on the lake bottom. And the first sensor that I'm going to talk about is called an acoustic Doppler current profiler. And this was deployed in 27 feet in 2022 and 14 feet in 2023. And this is an upward looking device. So it's measuring the currents, velocities, and the turbulence through the entire water column. And the second velocity sensor that we deployed is called an acoustic Doppler velocimeter. And this one is downward looking, and it's looking at a very small volume of water right at the lake bed. And we deployed this in 16 feet in 2022 and 9 feet in 2023. And this is measuring the current velocities right at the lake bed. In these pictures here, you can see red buoys. And on the next figure I'm going to show here, oh, sorry, I missed. In 2023, we also added GoPro cameras to capture underwater video. And back to those red buoys, when these pads are deployed on the lake bed, those red buoys create a goalpost that the boat driver could see when they were operating, and just to make sure that we were going directly over the sensors. The test boats. We tested a total of 7 boats combined between 2022 and 2023. And the boats covered three common recreational powerboat types. And those three types are a deck boat, bow rider, and wake boats. And these are boats that are commonly found in Minnesota lakes. The wake boats are specifically designed to create large wakes needed for wake sports like wake surfing. You see in the lower right corner there, there's a red rectangle. And what I'm just trying to show there is that these boats were unique in that they have external or internal ballast tanks that can be filled to add additional weight to the boat. They have trim plates, which can be adjusted to um, change the running attitude of the boat. And then there's wake shapers, which can make the boat wake itself um, different and put it in different scenarios that the surfer might like. 2022, the boats that were tested are the Hurricane deck boat that had an outboard boat motor, a Cobalt bow rider that had an inboard and outboard motor, and then a cruiser yacht. And I want to point out here that the cruiser yacht is a very large boat. It's a yacht, 14,000 pounds, 35 feet in length. And this is, I would say, not common on most Minnesota lakes. But there are a few lakes that would support boats of this size, and one of them being Lake Minnetonka. In 2023, again, we tested another deck boat, Starcraft with an outboard, a bow rider, the Sea Ray that also had an inboard outboard. And then in both 2022 and 2023, we tested two wake boats, one being the Nautique G23 Paragon, and the other one being a Malibu Wakesetter VLX. So Jeff briefly mentioned the different modes of operation, and what we did is we tested two different conditions. And the boats were tested under their typical modes of operation. So for condition one, that was all boats on plane or in planing mode, or sorry, planing mode. So 21 to 25 miles per hour. Condition two was for the non-wake surf boats. That was that displacement mode, that slow, leisurely cruising speed. And for the wake boats, that was the semi-displacement mode, or the mode that you would be in when you're surfing, which was right around 12 miles per hour. So to create these hydrodynamic phenomena, each boat was tested in a single day. And for each condition, the boats made 5 passes in a straight line over the pads. And the color lines that you see in the figure there are the real-time boat positional data that was plotted. And we have those for all boats and all the passes that the boats made. Between each pass, we had a 15-minute waiting period, and that was to hopefully be enough time to allow any of the velocities or the disturbances that we created through the water column or even at the lake bottom to settle and get back to a pre-pass steady state. And then between the two conditions, we had a 1 hour waiting period, again, for the same reasons, to just kind of let things settle and return to a steady state. And we always did condition one first, because we hypothesized that that would have the least amount of disturbance to the water column and lake bed. So with that, I'm going to turn it back over to Jeff to get into the data.
All right, you're seeing this? All right, this is the thick part of the presentation. We're gonna get into our data and results. And for those of you that have downloaded the report, you know it's a long report. and we're not going to be able to get, there's no way we can cover it all. So we really encourage people to download that report and read through. We're going to hit some high points here tonight. Okay, let's start with data analysis for the acoustic Doppler current profiler, ADCP. So a reminder, and I'll say this throughout, the ADCP is measuring, it's sitting on the bottom of the lake, it's looking upward and measuring the entire depth. And the first data set we'll talk about here is echogram. And this is essentially, think about a fish finder that's pinging from your boat to the bottom. This is looking upward and it's sending reflections back off of objects in the water. It does a great job of detecting a strong signal from the entrained exhaust bubbles, as well as the suspended sediment in the water column. We use that information to calculate average and maximum bubble depth penetration and the duration that it was in the water, and also used it to calculate average and maximum sediment resuspension height and duration. So what you're seeing in these two photographs on the left is a boat that you can see the bubble entrainment on the left slide, and you can see reflection off of that bubble. And the black line in there is where we mapped the boundary of the bubble plume. And you can also see that on the right side. On the right image, you also see how we tracked the sediment plume. This was one of the wake boats in surfing mode where it kicked up material off the lake bed, and the echogram was able to pick up that interface. So we used that echogram to do a couple things. One was to look at how deep the bubbles penetrated, and that's what this plot is. On the left is condition one, the boat's on plane. Each of these lines is an average of the 5 passes on that condition for each boat. So you can see that all the boats on plane, the bubbles didn't get much farther than 7 or 8 feet into the water column. Just to the axes here, depth is on the y-axis and time in minutes is on the x-axis. In condition two, where you've got cruising or surfing, you can see that in this case, the wake surf boats are purple and blue, and you'll see that we're consistent with our colors all the way through. So if you want to pick your favorite boats to watch, they're all the same. So purple and blue are the surf boats, and those the bubbles go substantially deeper. If we look at the results from the resuspended sediments, that's what this is here for the Nautique G23 condition 2. What you're seeing are the individual passes, the 5 passes in that condition, and each of the echograms reflecting back in our data sets. And so this is, again, the ADCP was positioned in the 2 seasons, and the first year was at 27 feet. So there was no evidence of resuspension by any of the boats tested. In the second year, when the ADCP was in 14 feet, only the wake boats in condition 2 or surfing showed suspension. The plot on the right is just the distribution of those 5 plots. So you can kind of look at the distribution of the maximum depth set for each pass. And so you can kind of see we saw material be suspended off the bottom up to 8 feet, 6, 7, 8 feet into the water column. Now we're going to move ahead to some of the other those phenomena that we introduced earlier. And again, I'm going to talk about both ADCP and ADV. Do your best to hang with us here. This is a lot of technical, but we think it's important for you to see the level of detail that we went in our analyses. And what I'm showing here is an example of a velocity signal that we would get back after it's been through some processing at this point. But what you're seeing is velocity on the y-axis, time in seconds on the x-axis, and you're seeing that signal, which is the velocity. And you see what was very common is that you would see an initial first 2, kind of a maximum, a minimum, and then you would see a series of oscillations that formed. And through our work, kind of early in the project, we were identifying what we see as the bow wave signal and a stern wave signal. And then the other stuff happens. In this plot, this is a plot actually where we don't have strong propeller wash signals. And so that's why we list it as transverse waves. But remember, our sensor is just measuring the velocity and it can't discern whether it's transverse or prop wash. And what we want people to realize is once you get past the bow and stern wave, both the prop wash and the transverse wave are interacting together. And the complex thing about waves is they actually sum up with each other. So we can have a transverse wave signal and a prop together. What we're going to measure is the combination of the two of them. So our job here in the analysis was to figure out how to separate these two signals from one another. And you'll see in the paper that we developed techniques for doing that so that we could look at the transverse waves separately from the propeller wash. We're not going to get into this here, but see the paper for details. So I'm using this figure to show that what we're gonna start with is looking at how we analyze the bow and stern wave phenomena, and then we'll talk about how we analyze transverse and propeller wash. So let's start with the analysis of the bow and stern. And we're going to start with the acoustic Doppler, which is the ADCP, which is again measuring the whole water column. And we include this figure here in the middle, which I showed before. We've got the hull displacing water. It's pushing water forward and downward into the water column. And when we get to the back of the boat in the stern area, water is able to recover and restore. It moves upward and backward. And the image on the figures on the right are an example of what that data looks like. Which I remember when I saw this the first time, it was really exciting to validate what we should have seen, right? So what we have here, and I'm going to define a few other things. When we measure velocity, we're breaking things down into horizontal velocity that's moving parallel to the water surface and vertical velocities moving up and down. And we look at that data separate from one another. So here we see the bow is actually, on the last thing I need to tell you is that the axes here go from a negative to 0 and then a positive. So positive is to the right. Our definition for boats, the direction the boat is traveling is positive. So in this case, the bow is moving positive forward horizontally. The stern is moving negative backwards, which is exactly what these vectors show in our schematic. The vertical velocities, the bow is in the vertical domain, positive is upward and negative is downward. So here, bow is moving in a negative direction, is pushing water down, and the stern is moving backward, upward. So that's always fun when your data shows you what the physics should be. If we then spend a lot of time looking at all of the signals through the water column, and what these two plots show are for condition 1 boats for both years. On the left is the 2022 campaign, 2023 on the right, and only the horizontal velocities that we're showing today. And what you can see is that the data is shown here in these solid and dashed lines, and then we fit regression lines to those as well. And so you can see that in general, the velocities are higher at the water surface and they decrease towards 0 as you get deeper into the water column. On the left side, we're looking at 2022, where the maximum depth was 27 feet. On the right, the max depth was 14 feet. I want to introduce one other thing. You'll see these dashed lines on either side of 0. Those are at 0.3 feet per second. And we did a lot of work trying to figure out some kind of a velocity of significance, a velocity threshold. And we determined that for this work, we were going to select 0.3 feet per second to work with. And that's a velocity that has been used by other people doing similar kind of work. Other research from lakes and river systems, and we settled on that velocity. By the way, this is a velocity that if others feel so compelled, you can go in and kind of tune that to your lake or your condition if you'd like. But for our condition, 0.3 is appropriate. What that allows us to do then is to take these velocities and find the point in elevation where the velocities decrease below 0.3 feet per second. And that elevation means that when you're deeper than that, the velocities are less than 0.3 or maybe below a threshold for motion, so to speak. So we use that. You'll see if you look at the paper, you'll see we use that 0.3 to kind of transfer the velocity profiles into a depth of impact. In this case, you can see that for the boats on plane, that all boats in both years, um, the velocities, cross that around 8 feet or even less. And so that would say that the velocities drop to insignificant or small values at depths, kind of 8 feet or less or 10 feet or less. When we look at condition two, which is cruising or surfing, depending on the boat, you'll see that, again, I'm only showing the horizontal velocities on the left of the 2022 boats. On the right is the 2023 boats. And again, 27 feet of water here. I should point out again, our colors of the surf boats are purple and blue. So there's a lot to look at here, a lot to explain in a short amount of time. The take-home message is if you look at in 2023, we're in 9 feet of, we're in 14 feet of water, I'm sorry, here. And you can see that the surf boat velocities were quite high, well above the 0.3 kind of threshold we selected. And that bears out in the video work that we will show you and that you've probably seen. Interestingly, you see that the stern has a bigger effect than the bow in this case. I think that's what I wanted to show on these. Let's move ahead. If we now look at the acoustic Doppler velocimeter, a reminder that this is the probe that's sitting at the bottom of the lake. It's measuring a single point near the bottom, just off the bottom of the lake. On the left plot, this is similar data that shows the distribution of the data that was measured, and the kind of the maximum horizontal velocities that were recorded at 16 feet of depth. And here is condition one for all of the boats. And then again in 2023 at 9 feet. And if we go to the, let's see, different. Oh, these were broken up. I'm sorry. Bow waves are shown here, and stern waves are shown here. So nothing too exciting going on here, which is great. And now if we move to condition two, where we've got cruising and surfing, we see some differences. The maximum velocities at 16 feet depth in 2022 of the surf boats, you see the velocities are higher. And you'll see even some thresholding we put in here to look at threshold of motion of different sand and silt sizes. And in the 9-foot depth, those effects are even greater. I'm going to keep moving. Let's move ahead to transverse waves. So transverse waves, what I want to show here is that we're focusing now, and this is a point where we've separated the transverse waves and the prop wash. We're kind of combining our measurements. We figured out a way to separate those. And we just have the transverse wave signal. And you'll notice that this is idealized, but in general, transverse waves, they decrease in their amplitude over time, but they stay a fairly consistent wavelength. And remember, for ADCP, we have the full water column of data here. So there's a lot of data. What we chose to do is, in 2022, select 3 elevations to examine carefully. And in 2023, we selected 3 additional elevations, and those are listed here. Here's what that data looks like for 2022. So 27 feet of water. And what we're plotting is the velocity amplitude. So we take the absolute value, because this is a fluctuating, oscillating velocities, we take the absolute value. And you see how these transverse waves decrease their velocity in time. Again, purple and blue are the surf boats, and then the non-surf boats are the other colors. And a reminder that the transverse waves are only occurring under condition 2. So I'm not showing you a condition 1 plot because there were no transverse waves. So this is surfing for the surf boats and cruising for non. And then you can see the different depths. The top plot is at 10 feet, and you see the velocities. We fit a regression line to these data. And as you get deeper into the water column, you see how the velocities change, the non-wake surf boats decrease, as do the surf boats, but they're still fairly high and stand out from one another. And down at 20 feet, the surf boat velocities of transverse waves decrease even further. Now in 2023, we were in 14 feet of water, so we're closer, the bottom's closer to that water surface. We expect the waves to be larger. Again, condition 2 here, the surf boats shown. It was really difficult to get data. There was so much energy in the water that data quality was poor for roughly the first 25 to 30 seconds. So that's why you're seeing data missing. The point here is, though, that there's quite a separation between non-wake surf boats and wake boats in these usage modes. The other point is that in here, we're looking at 8, 10, and 12 feet, and you see a fairly substantial decrease in those velocities just over that 4 feet. Now we move to the ADV, similar kind of approach. We're separating the data from one another, just looking at the transverse waves. Here we're looking at the horizontal velocities and the maximum values for condition 2. And at 16 feet of water in 2022, you can see the transverse wave velocities were slightly elevated for surf boats. In the 9 foot, though, 9 foot of depth at the bottom of the lake, the transverse waves were larger than the non-wake surf boats. Okay, let's round this out with propeller wash. Propeller wash, again, is a very complex phenomenon. In order for us to look at that, we again selected 3 different elevations to pull data in 2022, 3 additional elevations in 2023 data. And then what we did to help get our arms around this is to define 3 different times bins to do some averaging and look at 5 to 10 seconds, 10 to 30, and 30 to 50 seconds in the data. And this is what that looks like. Here is what the different data for prop wash looks like at 10, 15, and 20 feet of depth. These are the 5 passes of one of our test boats and their velocities. And what we chose to do is to bin these across these time intervals of 5 to 10, 10 to 30, 30 to 50 seconds, and do some statistical analysis of all of the data in these bins. And this just helped us get our arms around kind of the variability of pass to pass, but also capture some of the effects that are underway here. And this is what that data looks like. Again, you can spend more time if you go find the report. This is condition 1. So we're on plane, all boats here, and the time bins are in these different columns, and you can see the different velocities, and then the different rows are the depths. I'm showing only 10 and 15 feet here. The point of this image is all boats on plane, the propeller wash was fairly insignificant at these depths. So all boats show velocities well below 1/10 of a foot per second. If we go to condition 2, and this is in 2022 data, we see that the surf boats, which are these right 2 boats at 10 feet, you see their velocities were measured to be much higher. But that decreases as we get to 15 feet. And then in 2023, condition 2, so I didn't include condition 1, but here we're cruising and surfing. Condition 2, we're in 14 feet of water. And again, difficult to get data in the initial parts, but you can see that 10 to 30 seconds and 10 to 50 seconds, we see an elevated velocities in the propeller wash of the boats that are surfing. And then I'll round this out by just the ADV. We did the similar thing, a single measurement near the lake bed. This figure shows the separation of the measured signal in blue. The propeller wash is the refined signal out where we extract just the propeller wash. And this is what propeller wash signal was measured for the 2 surf boats tested in 2023. And note that in 2022, there was no significant prop wash measured at 16 feet. But in 2023 at 9 feet, we did measure significant velocities, and those are shown here. You can see a peak in the first 30 seconds and then a decrease in those velocities. So that's a lot of information. Um, and again, hopefully some of it made sense. We just encourage you to go take a look at the report for more information. So in summary, we successfully tracked exhaust bubbles, uh, bubble plume, and if present, suspended sediments. The ADCP measures the full column width. ADVs measure near the lake bed. The bow and stern pressure waves generated short duration velocities, and we used a velocity thresholding technique to determine impact depths of that data. Transverse waves and propeller wash velocities combined together in the measured data, so we developed methods to separate these. Transverse waves and propeller wash were evaluated at different depths to help determine how the velocities change with depth and time. And a final pitch to download that report and have a good read. All right. The last part of my section is to talk about the underwater videos. Um, they show a lot. We're excited that we were able to capture um, such nice videos. So we deployed GoPro cameras on those pads that Andy talked about earlier. And I'm going to show you 3 videos tonight from underwater. The first one is a condition 1, all boats on plane. And the bottom line is it's a similar story for all the boats that were tested in 2023. I should note we don't have footage for 2022. All we have is in the 2023 test campaign. So you'll see a quick bow and stern pressure wave. That's the main effect you're going to see in these videos. As that bow comes, you'll see the sediment and vegetation moves forward slightly and then backward um, as the boat passes over. And this is at 9 feet of water. So here we move to 14 feet. Here the setup is the boat is traveling overhead, the camera moving out into the distance. Let's see. You get lost in the videos here. Okay, the next video we're going to show is this is condition 2. So this is a cruising for the non-wake boats in displacement mode. And it's a similar story for the other non-wake boats in this condition. And again, you're going to see a very rapid bow and stern pressure wave. We don't see exhaust bubbles here. We don't see a lot of sediment resuspension, and there's no transverse waves that were observed here. Same view as before, 14 feet now. So I think what's interesting about those previous 2, what we think is interesting is that, and what was somewhat surprising is that the bow and stern, the bow and stern pressure waves, even under hydroplaning conditions, when the boat's on plane and in cruising, affected the bottom. We see the bottom move even up at 14 feet. It wasn't a lot of sediment, but you do see disruption of the sediment. Here we're going to look at condition 2 of the wake boat in semi-displacement or surfing mode. And we're going to see a lot of things happen. We're going to see the bow and stern waves initiate motion. So not just move it a little bit, but it's actually going to create a suspension. At 9 feet, we're going to see exhaust bubbles. You'll see the bubbles come down, but you won't see those at 14 feet. which by the way supports what we saw in some of our earlier data. The transverse waves and propeller wash will be observed, and you'll see a lot of sediment and vegetation moving. There's the exhaust bubbles. I'll just let this go for a little bit. So even 13 minutes later, we still see disruption. Um, so, so here's 14 feet. Again, the boat coming overhead. So I'll leave it there. I would just, if you haven't seen the videos, they're available through our YouTube channel, through our website, and others have posted them as well. So um, take a look. So the last thing we're going to talk about is the aerial footage, aerial video footage. We had a drone overhead. This video is from condition 2 of a wake boat in semi-displacement or surf mode. The same story was true for the Malibu boat. This is the Nautique G23. And I'll show just pass one as it comes through the 9-foot marker there. And now it's reaching the 14-foot location. And what you're observing is from the drone, we're starting to see suspended material in the water, and quite prevalent at 15 minutes. And if we move forward to, I'll show you the fourth pass here. You can see the plume is pretty well established after 3 passes. And so this illustrates, the importance, well, the importance of depth as a consideration when you're operating boats, when you're operating a boat in surf mode, as well as, repeating in the same location. So with each additional pass, we think there's resuspension. We observe that in our video, and that just builds within the water column. So with that, pass it back to Andy.
Is that sharing?
Yes, now it's sharing.
Is it in? It's not going into.
I see it. I see your view, not the presentation view.
Yeah, I don't. Slideshow. Hmm,
You might already have it open. That might be.
there we go. Now is it better?
Still the
Yeah.
same. I'm seeing the slide deck.
So you see the slide deck, but you don't actually see the presentation.
Well, I see your slides plus the slide deck. You know, it's like, there it is.
There we go. Technology. All right. I'm gonna get into our key findings here, give Jeff a little break from talking. Um, so we've been talking about the hydrodynamic phenomenon produced by recreational powerboats that have the potential to impact the water column. And the key finding there is that we've identified the bow and stern pressure waves, the transverse gravity waves, and propeller wash. The velocity magnitudes of these hydrodynamic phenomena and their extent, so that's the depth and duration, are, are tightly linked to boat displacement and the mode of operation that we've explained. The bow and stern pressure waves, they're the primary phenomenon or phenomena that initiate the movement of lakebed sediment. So that bow and stern pressure wave happens really quickly, on the order of seconds, and that's what initiates that bed to move. But it's really the transverse waves and the propeller wash that are able to lift and entrain that sediment into the water column. And Jeff went over a lot of data, and we do have a lot of data in this report. And if taken individually, each data set has its limitations. But if you look at all the different data sets, we do see multiple lines of evidence that can be used to inform science-based guidance for the minimum water depth that recreational power boats should maintain, during their typical modes of operation to minimize lake, negative lake impacts. So with that, we came up with recommendations, and I'm actually going to basically read them word for word right out of our report. So our recommendations are as follows. When operating in planing mode, it is recommended that recreational power boats, like the ones studied in our report, should operate in 10 feet of water or greater to minimize impacts on the lake bed. When operating in sustained displacement mode, so that's the slow cruising, recreational power boats like the one studied here should operate in 10 feet of water or greater to minimize impacts on the lake bed. Of course, at times, traveling in waters less than 10 feet is unavoidable. For example, getting to and from a boat launch or your dock, or maybe you're going through a shallow channel. And in these scenarios, it's recommended to go as slow as possible. It's not uncommon to see no wake zones. So just going as slow as possible to minimize the magnitude of the hydrodynamic phenomena that we've been discussing. Wake boats should operate in 20 feet of water or greater when in semi-displacement mode or surfing mode to minimize impacts on the lake bed. And then just finally, all boats have the potential to damage aquatic vegetation. And so in general, boats, and when you're out there recreation, just be aware of where aquatic vegetation is and avoid those areas to minimize disruption to that aquatic vegetation. Our report, we did put it through a technical review process, an independent technical review process by three subject matter experts in fields related to the research topic here. The reviewers had no previous or current collaboration with any of the research team and were identified as authors who have published similar research. And they volunteered their time for the reviewer role. So the process went as follows. Reviewers were provided a pre-final draft of our report and all the associated materials. So that includes our appendix and the videos and such. So we sent it to them. They provided their detailed feedback and critique. And then it took us 3 months to respond and address all the comments and incorporate them into a revised draft. We sent the new, final draft back to the reviewers and have them have an opportunity to review it and to provide additional comments. And they reviewed, or the reviewers all independently agreed that the authors had sufficiently considered and incorporated their feedback, and they approved the final version, which we published and is now publicly available. We want to acknowledge our funding sources. The It was partially funded by a crowdfunding campaign that was ran through the University of Minnesota Foundation. So thank you to everybody who contributed to this project. And then also we had funding from the Minnesota Environment and Natural Resources Trust Fund as recommended by the Legislative Citizen Commission on Minnesota Resources. And I'm not going to read all the names, but we want to thank all the individuals that helped to make this research possible. Just quickly, phase 3, it's in progress, like Jeff said at the beginning of the talk. We are characterizing the similarities and differences between wind-generated waves, including storm waves, and boat-generated waves. We've had sensors in the water last year and again this year. And we want to assess how different types of waves impact the near shore region of a lake. And our goal is to publish summer 2026. And again, that's funded by the ENRTF. And thank you for attending. And with that, I think we'll turn it over to questions.
Yeah. Great. Thank you, Andy. Thanks, everybody. So we'll move now to questions. Matt Luker, our colleague, we'll start with questions that were submitted ahead of when you all registered. So we've kind of distilled that down and developed some answers for those questions. Hopefully, a lot of this was answered in the presentation, but let's just dive in. And then I think what's going to happen now is, Bridget, do you want to say something about Q&A?
Yep, so I also opened up the Q&A function, which is at the bottom of your screen. So if you can use that little icon with a question mark, click that and type in your question. We'll get to as many of those as we can as well.
The other thing, just as a time check, we said 7:30. I feel like we went over. Maybe we allocate another 10 onto our Q&A.
Sounds good.
Okay, well, it sounds good. I will start this off. So as Jeff said, a lot of these questions the initial set of questions. I see the questions Q&A start coming in, but these initial questions are from your registration, and so try to hit on these. But some of these questions kind of really reiterate what we want to, hit them, make sure they hit home. So we'll just go through them one more time. So the first question is: the study is focused on wake surfing. How does wakeboarding compare? Jeff and Andy?
So sure, the study, well, I think the study was not focused on wake surfing. We looked at a lot of different boats and a lot of different uses. But I think to answer the question about wakeboarding, the way we think of it is it's done when a boat is on plane, and so the impacts will be similar to results of on-plane operation, like condition one in the study.
Okay, thanks. The next question we had, the next registration question we had was, did you test propeller wash during startups when boats are barely moving, i.e. when they're starting to get going, like when you start a skier or something like that?
No, we did not.
No, we didn't study that.
Okay, the third question we have lined up is, do you have a strategy to respond to adverse reactions from wake boat owners or dealers? It's a
Yeah, we
pretty
got
good
a
one.
few questions like this. I think we wanted to respond to this one. I think, we are, we respond to all stakeholders in an identical and consistent way. At least we're trying to. So again, the role of the university here is not is really to focus on producing robust and accessible data that can be used by various individuals and organizations interested in recreational boating and making informed choices. So the question kind of is phrased that we're um, in a certain camp, but I think we're really taking all our inquiries in the same way. Anything
Okay,
to add,
thanks.
Andy? I think that's
The next question is, what are the most successful tactics to convince legislators that limiting lake boat use could help protect our lakes?
I think similar answer.
Yeah,
It's not really our focus.
Yeah,
I'd say
we're not advocating for or against the use of wake boats in the sport of wake surfing.
I think
Okay,
we would encourage to the extent they are willing to do so to look at the science and read the reports for themselves rather than another group characterizing them. Um,
okay. The next question we had was, do pontoon boats damage lake beds, or how do they fit in this picture?
Yeah, I can take that one. We did not study pontoon boats. Future studies, yeah, it might not be a bad idea to include them. Because pontoons typically operate in slow cruising or on plane. I think the hypothesis would be that, their impacts are similar to the non-wake boats. Um, all boats, including pontoons, displace water and create, hydrodynamic phenomena in the water column. So, at some depth, they will have an inverse adverse impact to the lake bed if they're operating too shallow. Another interesting thing to think about is pontoons don't have hulls. They're pontoons that are sitting more on top of the water. So yeah, that would definitely be an interesting boat to include in a study.
Yeah, I would just add on that. I know just seeing pontoon lakes over the past, I don't know, 10, 15 years, they have really changed from a cruising boat to the performance pontoons you see a lot too. So there's a lot of variation among that. So it's hard to generalize pontoons in general. Um, the sixth question we had was, did you study personal watercraft impacts, PWCs, including tail walking, which is the wheelies, I guess, that Sea-Doos do, as well as normal operation?
Yeah, we didn't study that. Personal watercrafts were not covered in this project, but um, the tail walking that you mentioned of kind of doing a wheelie on your personal watercraft, I could see that being an issue with them being jet propelled and where that jet of water is going in the water column, how deep, that kinds of things. So yeah, I think that would be something good that a future study should include.
Okay. The next question was, your study shows effects from ski boats. evident at 10 feet of depth. How strong is the evidence that these effects are harmful to the lake? That's a very good question. For Randy.
Um,
I can take it if you want. I mean,
sure, I'm just
I
trying
think
to.
our data and study, consistently shows that bow and stern pressure waves from non-wake surf boats, including what could be used as ski boats, operating in, slow cruising or on plane resulted in brief disturbance to the lake bed at depths less than 10 feet. Um, it's a real effect. We see it in the videos, and it's consistent. So I would say that it is, there's strong evidence. Again, they're very short duration, those bow and stern waves. And
Okay.
yeah, I don't know if you have anything more to add to that. Yeah.
No, that's good.
Sorry, we're just trying to keep our eye on the Q&As coming in as well at the same time. So uh, the next registration question was, how were the variables of the study chosen?
Yeah, I remember this question. Hopefully the webinar clarified it. I think this is a hard one to answer. I mean, it's unclear what, the way we do project design is complex. We're looking at the problem. We're a hypothesis-driven group. We're also working on a real body of water with constraints, and so all of that pulls together to kind of isolate the variables we're able to study, try to minimize those variables, try to decide on instrumentation that can capture um, and test our hypotheses. So um, maybe we'll just leave it at that, and hopefully the seminar covered that.
And if it didn't, I would just point people to the report.
Yeah.
Pretty detailed.
Okay. Um, Next question was, given uneven lake contours, why not double your recommended minimum wake depths or give some sort of safety factor, I guess they're getting at.
Mm.
And then the second one, do wake boats have depth alarms? Is that something they already have, or can the user set up?
I think that the answer here, I made a statement at the beginning. We're not, these recommendations and guidances are out of the data, so they're not considering what a management group might think about in terms of implementation or um, enforcement, things like those other considerations that someone might take in. They're really drawn from the data and the multiple lines of data. As far as depth alarms, I'd say most boats that I'm aware of this caliber have depth finders on them that are continuously reading. Um, some of the boats I'm on, those things don't work when you're going fast. So I would think though most modern boats have ability to measure their depth in real time. The other part that's kind of related to this is, what are the quality of maps out there? And I think that's a question that groups need to wrestle with is, if you look at some in Minnesota, the lake finder information isn't always accurate, but I know some of the fishing downloadable maps that you can get are very accurate. So I think what might become coming here is a better awareness and accurate mapping of our lakes so we can be mindful of the water depth.
Okay. Um, I guess the next one is why the big gap in testing between the 16 and 27 feet of depth? The big gap in testing.
Yeah, I hope that's clear now that at the 27-foot depth, the ADCP was looking at the entire water column. Also at the 16-foot depth, the ADCP was looking, or I think they're referring to the first season, so 2022. So the 16-foot was the ADV looking at the bottom, and the 27-foot, the ADCP was looking at the entire water column. So I don't think there is a lack or a gap in data.
Oh, okay.
We captured the water column.
Okay, no, that makes sense. That may be a misunderstanding of what the ADCP does, actually measures the full height. Yes. And I think that was covered pretty well with some of the graphics you guys generated during the presentation. Um, is the water depth based on average, median, or actual spot measurements? The water depths.
Yeah, they're at the specific sites. So the 9 foot, 14 foot, 16 and 27 feet, they were actual spot measurements, like physically going out there and measuring the depth.
Okay.
So it's not an average, it's not um, a median or anything like that. I don't know if I'm answering the question or interpreting the question right.
No, I think it seems to be like it's yeah, the measurements were taken at the actual spot where the instrumentation was, I think is what the response is. That would answer the question. Um, the next thing is, does motor size affect the sediment disruption or wave strength?
Hey, Matt, you're the best to answer this, but I think I'd say the answer as the question's written, motor size does not answer the question. It's far more complicated. It's the mass of the boat, the weight of the boat, and how it's used, and and then what the size of the motor prop need to be to the thrust in order to push that boat. So it's more complicated than just saying boats of a certain size have this effect.
Yeah, yeah, I definitely agree with that. That more resistance for wave making resistance or motor drag is going to require a bigger motor. So it's really a factor of what the hull of the boat is imparting. And
Yeah.
um, another impact is that once it gets that these yeah, when they're dragging along at these inner semi-displacement modes, there's a lot of wave making resistance, and so that requires the bigger motor, which thus increases the amount of prop wash or the energy just put into the flow. So yeah, I'd agree with that.
The next two are similar.
Yeah, so the combination of some lakes have silty, mucky bottoms and some have sand and gravel. Did you look at the differences in impact based on the substrates? And then the similar question was, did your study cover different substrates? So I guess, did we look at different substrates and what would be the different impacts with different substrates? I guess it could be a good combination of those two questions.
Andy, do you want to take that?
Yeah, I can, I guess, take the first part of that. The ADV sites, actually both years, so 9 foot and 16 foot, the substrate was sandy gravel. And then uh, in the 14 feet and 27 feet, so where the ADCP was, both those sites were more of a mucky um, substrate, detritus or dying organic matter in various states of decomposition. Um, I think it's probably safe to say that when you're looking at resuspension or the ability to mobilize the lake bed, that your organic material or your mucky material is going to be easier to resuspend than, let's say, gravel or coarser sand. Jeff, I don't know if you want to touch base maybe a little bit on where sediment settles. We want to get into that, or just probably save that
Um,
phase
I
three.
think we save that for see. I want to see what's online too here.
Yeah,
Um,
Um, yeah, while you're looking at that,
I think you could skip down to under 18. Looks like would be a good one, Matt.
okay. Explain. Can you give an explanation why you compared one of the largest surf boats, the G23, to one of the smallest Sea Rays? So the G23 is 7,200 pounds and the Sea Ray is 3,500 pounds. Wouldn't an apples to apples comparison be more appropriate?
So in all scenarios, we compared a large range of boats, including, all the way from the deck boats, which are lighter recreational boats, in the, 2,500 pound range, all the way up to that very large cruiser yacht, which was 14,500 pounds. So if you look at our results and our figures, we're comparing all the boats. So it's not just comparing a wake boat to, just the Sea Ray, for example.
Um, Let me see if I can probably jump over into the question and answer online. Let's see here. Um, some of these are just. Did you target a particularly calm day to do the testing to avoid wind storm wave interactions?
Yeah, yep. We attempted as best we could to deploy and test on days that were not windy. Yep.
Okay. Yeah, I do remember waiting for a nice weather day and having to drop
Yeah, it
everything
was.
up there.
Yep.
Um,
You can just, if you want to just go in order, Matt, too. I
uh,
don't know.
uh, guys see any on here?
There was a couple
Didn't, I
questions,
guess why
couple questions
didn't
on,
we look?
oop, that Matt breaking up.
Yeah, Matt's breaking up.
I'll just go ahead with one that was submitted ahead of time. There were a couple about fish. So the question was, what is the impact of wake boating on fish health and spawning beds? And a second one asked, kind of inquired about our phase 3 work. And I think, um, our response is that fish and fisheries and is very complicated. To be clear, we did not look at impacts to fish habitat, and we need to be really clear about that. That said, I think you can, the the things that are evidenced in some of the videos. I mean, I think there's a lot of harm that's happening to those systems, but what the true impact of a lot of resuspension and so forth on habitat is something we did not study and can't comment on. Um, and then I think that the comment about phase 3 and can we include fish habitat, we take that as, fish health is a concern for people. I would say that's when we talk about it in our group, it's a big topic. It would require kind of a whole fully dedicated study and probably additional members to our team to address, and it's something we can look at in the future. Matt, are you back?
I am back. Sorry about that.
There's a
I
good one that
guess
there's a are the depth recommendations offered limited to depth to lake bottom, or could it also apply to depths to the top of vegetation? Um, our recommendations are based off of lake bottoms, so distance from lake bottoms, but it very well could be um, distance from the top of vegetation if, let's say, a manager, a resource manager, wanted to go that route. But that's not what our recommendations are saying.
Maybe I kind of want to go in order of the questions just so we don't miss anything.
okay.
The first question, and why didn't you look at startup impacts or the impacts of turning? And I think you partially answered that before, I think, but there's only so much you can do with a grant. I think it's an interesting question of startup, but here we looked at kind of steady state conditions. Um, John Bent sent in a question about this new study released in Wisconsin showing lakebed resuspension at 25 feet. The study showed video evidence. Um, and I would say we have been focused on putting this talk together. So I think we need to go review that. And tonight we just wanted to focus on our work.
Um, think this one from Michael Linden had been covered about the 0.3 threshold is for fine lake sediment. I think you guys did cover that pretty well about you just have to go to those figures in the chart and find your own threshold that you'd like to
The one thing,
use.
Matt, people can, I don't think they're able to see not everyone can see the question, so we should read them.
Okay. Um, this, this may already be in registration queues, but questions? But the 0.3 feet per second threshold was for fine lake sediment. So these are it's a broad stroke to use. And what if they had smaller sediment sizes or other materials? How would those recommendations need to be adjusted? I guess, and the answer was just have to find a threshold for yourself, I would guess, right, Jeff and Andy? And
Yeah,
then
and I don't
go to
know
those charts, like you said.
if Jess and Bill want to add too. They're welcome to, but yeah, there's um, the data is there for people to work with, and yeah, lakes are very different, and there's different, it's not uniform across the lake, right? And I think the comment that we bring up here is that lakes are sorting their sediment load, and that's going to be lake by lake and what the bathymetry is like. Um, and in what's happening is finer material is getting to places where it can't be disrupted. Once it takes a long time for fine and light material to settle, so it's going to find places in the lake that where there isn't energy for it to be disrupted. And the challenge with if we disrupt it by, for example, using our boats differently or increasing the power of our boats and how deep they go, we can reignite that sediment up into the water column. Um, and what are the implications of that? We write about it. We've talked about it. It's, turbidity, negative impacts from elevated turbidities. It can be nutrients in the water leading to algal growth and blooms. So that's kind of an overview of that.
All right, Kathy Erickson asked, why did you conclude that the 20 feet of depth is enough when the 14-foot depth was rather significant without doing additional measurements at greater depths? So the video was at 14 feet, and how'd you end up at 20?
We did do measurements at greater depths. That was the ADCP at 16 feet and 27 feet, looking through the water column, looking at the velocities. So we know what the velocities of the bow stern, transverse wave, propeller washes through the water column. So again, it wasn't looking at one specific data set, it was looking at all of the data and to come up with our depth recommendations.
Thanks for that, Andy. So Dennis, did you measure the width of the impact rather than just and I think the answer to that is we did not. We just had these single vertical measurements. And the drone view showed got to answer 10 to 20 times of the boat width. So yeah, we just didn't look at the width of the impact of the prop wash. David Johnson said, nope. Is there any video at 27 feet? And we do not have that. Is it correct to assume there are two concerns that may be distinct? Environmental impacts, number one, for environmental impacts based on underwater hydrodynamics, and number two, potential damage to persons and property from wave energy related to proximity to shoreline or other vessels. I think that's what we've been trying to get at, and then but with the two different impacts, one with the phase one report and this with the phase two report, right, Jeff and Andy?
Right. We haven't studied anything related to damage or injury to persons. So can't speak to that. But yeah, we did look
Um,
at energy with distance from boat toward shore. that was just characterizing. There does need to be additional research that's looking at environmental impacts of those diverging waves towards shore.
Okay. Um, Steve asks, what impacts will lake boats have with larger horsepower and greater size? I I don't know, but
Mhm.
Yeah, I think
I
that's
would imagine they'd be larger impacts.
Mhm. Yeah, would you say, Matt, it's going to come down to the thrust, right? At the end of the day, you have a bigger boat requires more thrust to move. We would see that thrust increase the prop wash effects. Now, this assumes that the technology of the boats aren't changed or evolve um, to mitigate some of this, but um, we haven't studied it directly, so we're just spitballing here. But I'd say not so much larger, but to maybe I would say, Steve, heavier uh, would 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 bring larger horsepower, and we would see increased impacts.
I mean, we at the time of the study, 2022, 2023, we were testing the latest um, wake boat in terms of horsepower, so 600 horsepower and weights up around 10 to 12,000 pounds with full ballast. Um,
And we did have two different size boats here, and I think they were larger impacts for the larger boat as well, I would say.
Just chiming in, I think we have time for one more question, and then the rest, um, the researchers will answer in a different recording and post that as well to the website.
All right, the last question we'll get to is Scott Kirk's asking, where did we get the data that says prior to wake surfing boats, they didn't travel at mid-plane or semi-displacement modes and only at slow cruise and plane? Um,
Sure. I think that's my comment. I said at the beginning, typical use wouldn't put boats um in a transition. And I think that's just our experience and interviewing and talking to others. So there's no reference to give. Um, so whether that's correct or not,
Another
I think it's fairly true though.
another thing to add is that we didn't directly test wake boats in the slow displacement mode, but if their ballast tanks are empty, um, and they're not using wake enhancing technologies, they would fall into the same category as non-wake boats in terms of our recommendation and being in 10 feet of water or greater to minimize impacts to the lake bottom. And we do talk about that in the report.
okay, I think we're reaching 7:40 here. Are we
I think we should wrap up. Bridget will capture these remaining questions and um, post responses to everything, I think, is our plan.
Yes, so thank you everyone for joining and for staying on for a evening packed with information. We hope that you come away with new insights and perspectives about recreational boating. And if you just to repeat, if you have other follow-up questions for this research group, please email us at healthywaters@umn.edu. And then again, a reminder that we will be posting this webinar to the Healthy Waters website in a couple of weeks. We will also be posting the Q&A and including the questions that we didn't have time to get to tonight. So if your question was not answered, check the website and it will appear there in due time. Thank you.
Thank you, everybody.
Thank you.
Good night.